Hello everyone, welcome back to the channel. In this video, I'm going to discuss the operating principle of transformers in detail, followed by the ideal transformer, EMF equation of the transformer, and the phasor diagram as well. In the previous video, I had introduced the working principle of the transformer briefly. So let's discuss that principle in detail over here. If you haven't checked that video, you can check and you can find about the basics of transformer and the constructional details. For understanding the operating principle of transformer, we are considering a core type transformer, and in core type, for understanding purpose, we represent one winding on one limb and second winding on the another limb. So the winding to which we give the supply, that is known as primary winding. Let's say this is the primary winding, and the voltage supplied is V1. Dot is marked over here to show the dot convention, and this is how the current is flowing, I1 current. And here we have the secondary winding. This one is a switch. When we close it, then there is flow of current through this winding, otherwise there is no current in this winding. This is the load impedance. Now the working principle of transformer is that when we give the supply to the primary winding, there is a current in the primary winding since the circuit is closed. This current is flowing through N1 number of turns coil. So therefore we have MMF N1 into I1. So that MMF leads to flux which will remain confined to the core, since core has very low reluctance. The direction of flux is upward direction. Flux phi is produced. Now this flux phi is linking with the second coil as well, leads to an induced EMF in the second coil as well. So that's how the energy is transferred, and the transformer operates on the principle of electromagnetic induction. There is no connection between the two windings, but there is transfer of energy from one circuit to another circuit by electromagnetic induction or through the transformer action. Now the induced EMF on primary side is denoted by E1. This terminal is positive and this one is negative. Similarly, we have induced EMF E2 over here. So current I2 will flow when the switch is closed, like this. Otherwise, I2 is 0. So I2 is 0 with switch open. Otherwise, it will have some value. So how energy is getting transferred? We have input voltage leads to flow of current I1, which leads to MMF N1 into I1, and then we have flux phi. That flux phi links with the second winding as well. So there is an induced EMF in the second winding, which will give us the value of current I2. Now what we see over here, that this V1 and E1, they are of opposite nature. They This is due to Lenz's law, because E1 is produced because of V1 only. So the response is opposing its cause. Now we can find out the value of E1 and E2. Now this E1 and E2, their value can be found by using Faraday's laws. As per Faraday's law, induced EMF is equals to minus N d phi by dt. So let's say phi is given as phi max sine omega t. So we can find out value of induced EMF in the primary as well as in the secondary coil. In primary, E1 will be equal to minus N1 d phi by dt, and E2, the induced EMF in secondary, will be equal to minus N2 d phi by dt. Now since the flux is common for both the primary as well as secondary, so phi is remaining same in expression of E1 and E2. So E1 will be equal to minus N1 d phi m sine omega t by dt. So minus N1, phi max is constant. Now when we differentiate this, then differentiation of sine omega t is cos omega t into omega. So the expression becomes minus N1 phi m cos omega t, which we can write as N1 phi m omega sine omega t minus 90. So similarly, we can write E2 is equals to N2 phi omega sine omega t minus 90 degree. Exactly same steps, only difference is that we have number of turns N2 on the secondary side. So this N1 phi m omega is E1 max sine omega t minus 90. Similarly, E2 is E2 max sine omega t minus 90. So we can write E1 max as N1 phi m omega N1 phi m 2 pi f. So E1 max is 2 pi f N1 phi m, and similarly E2 max is 2 pi f N2 phi max. Now we can find out the RMS value of induced EMF since RMS value is E max by root 2. So E1, that is the RMS value of induced EMF in the primary winding, will be root 2 pi f n1 phi max, and RMS value of induced EMF in secondary will be root 2 pi f n2 phi max. Now if we take the ratio of E1 and E2, then E1 by E2 comes out to be N1 by N2, which we write as A. N1 upon N2 is equals to A, and this N1 upon N2 is equal to A is known as turns ratio. Is known as turns ratio. Now moving on to ideal transformer. Now ideal transformer is the transformer where we will have certain assumptions in comparison to the practical case. So there are four assumptions for an ideal transformer. First one is the winding resistance is 0. Though this is practically not possible, but this is assumption that the winding resistance is 0, but practically it will have some resistance. Second assumption is that there is no leakage flux. Again, this is not possible, though the core is designed with the maximum possible permeability or high permeability so that it results in the minimum reluctance path, but still there is possibility of leakage flux and it will be there, but assumption is that there is no leakage flux. Third assumption is that core is lossless. There is no core losses, means the hysteresis as well as eddy current losses are 0. Again, it's not possible. The core is designed to reduce the hysteresis as well as core eddy current losses, but it's not practically possible to have them as 0. And the last assumption is the magnetizing current is negligible or small negligible magnetizing current is required to produce the working flux. Fine. Again, this is not practically possible. Still, this is the assumption. Now, based on this assumption that winding resistance is 0, then what we get from here that V1 and E1 they are equal in magnitude. Also, the induced EMF same will appear as voltage across this load when the switch is closed. E2 and V2 they are equal. So what we can write? We can write that E1 upon E2, which is equal to N1 upon N2, is same as V1 upon V2. Now based on these assumptions, we got E1 upon E2 equal to V1 upon V2. This is equal to N1 upon N2 equal to A, that is the turns ratio. Now let's draw the Phasor diagram of ideal transformer at no load. No load means the switch is open and there is no current on the second secondary side. The I2 is 0. We have induced EMF in the secondary winding, we have induced EMF in the primary winding. And what we have seen that V1 and E1, they are equal in magnitude but their direction is opposite. V1 is equal in magnitude with E1 but minus of E1. Minus of E1 because of Lenz's law, while V2 and E2 they are same. So this V1 equal to minus of E1 means that the power flow because of V1 is opposite to power flow because of E1. So that is what we mean by V1 is equals to minus of E1, though they are equal in magnitude. So in phasor diagram, we have to represent that phase difference. Now in transformer, on primary and secondary side, flux phi is common. So flux phi is taken as reference since the current which is very small or negligible, that can be shown like this: a very small amount of current Im which is required to produce a working flux, and obviously it will be in same phase with the flux, so a very small amount of current. Then we have induced EMF in the primary as well as secondary. So in EMF equation, what we have seen that E1 is equals to Em sine omega t minus 90, while flux was phi m sine omega t. So it means whether it's an induced EMF in primary or induced EMF in secondary, both are lagging behind the flux by 90 degree. E1 and E2 both are lagging behind the flux by 90 degree. Now depending upon whether it's step up transformer or step down transformer, we will have the value of E1 and E2. In this case we can say E1 is more than E2, so this one is representing like a step down transformer. Since V1 is equals to minus of E1, so it will be represented over here V1 equal to minus of E1. Again, to understand that why V1 is equals to minus of E1, this is because of the fact that E1 is the response because of the cause V1, and as per Lenz's law, response opposes its cause. So that's why E1 opposes the voltage V1, or other way to say this is that if we assume that both V1 and E1 they are acting alone, then the power flow because of V1 is opposite to the power flow because of E1, that we can even see over here. Because of V1, we are saying that current is flowing in this direction. If we just forget about this, that V1 is over here, then we have a, we have an induced EMF E1 over here. So this E1 can be represented like a source, this, like this source E1. So because of this, current will flow in this direction, which is just opposite to this one. So obviously the power flow because of E1 is just opposite to the power flow because of E1. So this is why they are represented in phase opposition in the phasor diagram. Now, if we consider that the transformer is now loaded, when transformer is loaded, it means I2 is not 0. So this switch is now closed and I2 will start flowing over here. So when I2 will start flowing over here, so what will happen? We have N2 number of turns for the secondary. There is another MMF N2 into I2 in on the secondary side. Now because of this MMF, what will happen? There is flow of flux. We can find out the direction of that flux. Let's say that flux is phi 2. Since current is flowing in this direction, by right hand rule or by the screw rule, when we try to find out the direction of flux, then the direction of flux is like this, phi 2. So which will oppose this flux phi. So when it will oppose this flux phi, so obviously it will reduce the working flux. So when the working flux will reduce, both induced EMF E1 as well as E2, which are proportional to phi m, they will actually reduce. So if this flux phi will reduce because of this flux phi 2, which is opposite to this, the maximum value of flux which is linking with this core, that will reduce. When this will reduce, then E1 and E2 both will reduce. So if E1 will reduce over here, so we had equation that V1 is equal to E1. So this balance will not be there. V1 will be more in comparison to E1. So when V1 is more than E1, because of the potential difference, more current will start flowing on the primary side. So we have one additional current over here, which will be denoted by I1 dash. So this I1 dash is known as load component of primary current. Since this one flows only when there is flow of I2. Now this can be represented in the phasor diagram. And what's the value of this I1 dash? This one is actually dependent upon I2, or we I1 dash must produce mmf on the primary side, and hence the additional amount of flux to cancel out the effect of this phi 2. So the mmf on the secondary side is N2I2. Since the reluctance is same, two mmfs must be equal in order to produce a constant flux in this, so that phi 2 can be cancelled out by the additional amount of flux produced by this additional mmf. So n1 into I1 dash, it should be equal to n2 I2, or we can find out the value of I1 dash as n2 by n1 into I2. So when we draw the phasor diagram, again we have to start with flux phi, a negligible current Im, E1 and E2 lagging behind this flux by 90 degree. V1 is equals to minus of E1. If we assume that we have a lagging power factor load, and I2, this is angle theta 2, then I1 dash, it's at 180 degree to I2. The magnitude can be calculated by this equation, but it should be at 180 degree. Why 180 degree? Because the working flux produced by both they are in opposite direction. It means both the currents are also in opposite direction. This I naught, sorry, Im, which was flowing even at no load, is denoted by I naught. I naught is no load current of the ideal transformer, which is equal to Im in ideal transformer. This is equal to Im only in case of ideal transformer. We will see that how it gets modified in case of practical transformer. This one is equal to I naught, and the resultant of these two currents is I1, which is the primary current. So I1 is phasor sum of I naught and I1 dash. Now based on this, we can even draw the equivalent circuit of ideal transformer. Since we have assumed that there is no winding resistance, there is no leakage flux, so we have voltage source on primary side, and in the winding we have induced EMF E1, current is I1, and on secondary side E2 EMF is induced and the circuit is closed. We have load impedance over here and current I2 is flowing like this. So this is the equivalent circuit of an ideal transformer. In the next video, I will start with the practical transformer aspects, considering all assumptions one by one. If you find this video useful, please consider subscribing the channel and do share it with your others who need to understand the transformer. Thanks for watching the video.